Greetings and welcome, friends. Mr. Waddy here. We are doing part two. Really, it's like, if you think about these in two parts, the first part was like 20%, not even of the lesson. So you're getting the bulk of this lesson right now. This is a good deal. You signed up for something great right here. We're talking about transformations of graphs of linear functions, and this is section 3.6 of the Big Ideas book. And here we are, we're talking about reflections. So maybe when you're done this video, you can just like take a couple moments and just like reflect. Oh, no. My internet friends are not lolling. My real world friends, I don't know, I like to pretend you guys are my friends, but yeah, you guys aren't laughing either, that's fine. Here we go. A reflection is a transformation that flips a graph over a line called the line of reflection. All right, so if I want to reflect in the x-axis, what I would do is opposite the entire output, opposite the outputs, opposite the y's, if you will, and it's being reflected over the x-axis, right? So this got flipped there, and this got flipped up there. It was a mirror, okay? I guess those arrows kind of almost look like it's rotation, so I don't want to imply that. But this point is now down here. This point is now, sorry, I did it wrong. This point is now up there. There we go. Everything got mirrored, right, is what happened. And the way you have a reflection occur is if you opposite your outputs. So multiplying the outputs by -1 changes their signs, right? So if this was like 3, 5, now it's 3, -5. Just the output was changed. If I want to reflect over the y-axis, all right, I do that by oppositing the x. Notice this was opposite to the entire function. This is an opposite of the x, and then plug that into the function, all right? And that is a reflection over the y-axis of the graph of the original function. So now this point gets mapped over to here, and this point, or I'll pick a slightly different spot, this point would have gotten mapped all the way over here. It's just that got reflected like so. And so multiplying the inputs, or the x's, right, are the inputs, by -1 changes their signs. So if I wanted to think about this as the point 3, 5, that is now located at -3, 5. So the x values, they done got flipped. We be flipping tables in here. So let's see. Let's do example 2. Example 2. Whoop-de-doo. Here we go. I think I gave myself 2 graphs for this. I guess I could have done it in 1. Nah, I'll do this one in 2, and then some of the later ones I'll do in 1. So let's see. Reflections in the x-axis and the y-axis. All right, here's my original function, f of x equals half-x plus 1. What is the slope of that function? It's in y equals mx plus b, or f of x equals mx plus b. What's my m? No? Anybody? Where's the m for this line? 1/2 is the slope. You're going up 1/2. Let's see, and what is my y-intercept? Is the 1, yeah, the positive 1. So if I want to graph this, the y-intercept is at the 1, and the slope is 1/2, so it's going to go up 1 and over 2, up 1 and over 2. It's not as steep as you could have it because it's a fractional slope between 0 and 1. All right, so let's see. Let's draw this line. Where's my... There we go. I just had to, like, you know, like when you pull start a lawnmower, it takes sometimes a couple times to get it going. That's all. I just had to pull start my graph there. So here's my original line, something like that. All right, watch this. I'm gonna cheat. Watch how quick I can graph this again. and let's copy it and let's paste it, and we'll pull this down. And look at, I just graphed. Oh dear, what did I do, friends? I scrolled too far. Oh dear. Oh, and now my mouse died. Oh my goodness, guys, this is terrifying. Ah. This is so professional. Okay, wow, all right. I was trying to show off with how quick I could draw that line, and then I broke the universe. My apologies. So here's our original line, and now they're asking us to graph g of x. I'll make that orange for g of x is equal to the opposite of my outputs. Opposite of my outputs. So what does that look like here? That's going to reflect over the x-axis. All my y values are now negative. All right, so this one would have been down here now, and this one would have been down here now, and this one would have been up here. And like this one here, that was 4 underneath, now it's 4 over. Okay, so oppositing the outputs is a reflection over the x-axis. It gets mirrored, so to speak, and here's my new function, like so. All right, so this would be g of x, like so. Cool, cool. If I wanted to think of that in terms of oppositing the function, it would have been g of x is equal to the opposite of this whole thing. And notice what would have happened if I distributed that minus sign. That would have been negative 1/2 x and minus 1 for g of x. All right, now I don't want you to have to like reconstruct these functions. I want you to think about them in terms of transformations, not just in terms of let me do a bunch of algebra to it. But notice the y-intercept is at -1, and that's where that is. And the slope was negative 1/2, and notice down 1 over 2, down 1 over 2. So the transformation seems to work. Good stuff, good stuff. Let's go over here. What if I opposite the inputs? Now they're claiming that that would have been a reflection over the y-axis, right? So the x's are opposite, so 0 would have gotten mapped onto itself. Here was this had an x-coordinate of 2, so now it's going to have an x-coordinate of -2. This one had an x-coordinate of 4, so now it's going to have an x-coordinate of -4, right? This one over here, this has like an x-coordinate of what, like -6 or something? I should count that out. 2, 4, 6, and so now it's going to have an x-coordinate of +6. So let's draw that line. Oddly enough, happens to still have the same slope. But notice these are not, the blue line and the orange line are not the same. They have different y-intercepts, even though they ended up having the same slope. Okay? So yeah, so that works out. Let's see if I did calculate t of x by plugging -x in for the original function's x. Let's look at what that would have been. So that would have been 1/2 of, and instead of x, I'm plugging in -x, or the opposite of x is the more appropriate way to say that, plus 1. What would this have become? Half of -x is -1/2 x, plus 1 is unchanged, and so t of x has a y-intercept of 1, ding ding, and a slope of -1/2, down 1 over 2, down 1 over 2, down 1 over 2. It worked out. The transformation worked, friends. Wow, amazing, amazing. Let's see, I don't think I need to practice more examples like that. Let's talk about stretches and shrinks. Here we go. These ones are gonna be crazy. Just you wait, it's gonna be great. All right, let's see. Shrinks, which by the way, I'm just gonna correct this and use my math on the street word. Schmooshes. There we go. Now it's correct. Make sure you guys change that on your notes, because who knows what a shrink is? What's no one? Schmooshes. That's how we really talk about these things. But also, if you like go to college to like be a math major, no one's gonna know what a schmoosh is. So I apologize, like day one of college, like let's flash forward like 5 years from now. You're in college and you show up in class and you're like, oh, that's a horizontal schmoosh. And then everyone's going to laugh at you, but then you'll be like, Mr. Waddy. So I'm sorry. But here we go. Stretches and schmooshes. I don't know. You can transform a function by multiplying all the x-coordinate inputs by the same factor of a. When a is bigger than 1, the transformation is a horizontal shrink because the graph shrinks towards the y-axis. And now that's the weird thing. I'm multiplying the inputs by a number bigger than 1, and it schmooshes it, which is not what I would have expected. Let me, actually, just for our internet friends, let's show them this little thing that we were playing with earlier. Let's see. So if when b, in this case, is my multiplying the x by something, the input by something, if I multiply b by a value bigger than 1, notice it horizontally smooshed it, right? And if I multiply b by a value less than 1, or between 0 and 1, notice it horizontally went and like pulled the orange point, pulls it horizontally. That's what was happening there. And so that's what's being described here. Shrinks towards the x-axis. When a is between 0 and 1, the transformation is a horizontal stretch. And notice the stretching that we see whenever I have a value of b that's between 0 and 1. It's pulling it to the left and the right. Okay? In each case, the y-intercept stays the same. Yeah, notice, oh yeah, it happens to be hitting the same spot, even if it was shifted. Never mind, I can't do that because my original wasn't shifted by that. But yeah, it's, well, actually, yeah, I'll show it this way. Yeah, notice that my stretching and smooshing it is not changing where it's crossing the y-axis, which in this case is 1.3. All right, let's see, we'll bring that back maybe. Bring it down, bring it around town even. Technique, Squidward, technique. You can also transform a function by multiplying all the y-coordinates or outputs by the same factor of a. When a is bigger than 1, it's a vertical stretch. When a is less than 1 or bigger than 0, the transformation is a vertical shrink. So let's see, let's bring our b value back to normal. And when I multiply the entire function by something, it's pulling it up when it's bigger than 1, and it's pushing it down when it's less than 1. Right? Good stuff. Good times. Good times. And so yeah, so those are horizontal and vertical stretches and smooshes. And here's another way for you to see it. Actually, that's weird. It did the weird like image showing up behind ghosting that I see sometimes. I don't like it when my screen capture ghosts. Here we go. So yeah, same idea. Notice horizontally, when a is bigger than 1, it's a smoosh. When a is greater than 1, it's a stretch. Or sorry, when a is between 0 and 1, it's a stretch for horizontal values. The opposite of what you would have expected, right? And then for vertical, it does it exactly as you'd expect it. If you multiply the entire function by some number, it's a stretch when it's bigger than 1, and it's a smoosh when it's between 0 and 1. So let's put this to work, friends. Let's do an example. I've got example 3 coming for you and me. Here we go. Horizontal and vertical stretches. For the function f of x equals x minus 1, question, what is the slope of that? Is it 0? Oh, you good save. Good save. Remember, there's always a 1 hiding there, like a hobbit wearing a ring in front of your variable if there is no number written. So that's a 1. Oh, you almost got me there, Bilbo Baggins. And let's see, the y-intercept, which I don't use green, I use red. Come on. What's the y-intercept for my original function? -1. We're getting this. So let's see, slope of negativo 1 is right there. Sorry, y-intercept of -1, slope of 1, so up 1 and over 1, up 1 and over 1. Here we're doing it. We're having fun. Up 1 and over 1. So let's see. Let's giraffe this. So draw the line like so. So there's my original function. Let's graph its friend. So let's see. This is multiplying the input by 1/3. Multiplying the input by 1/3. So g of x multiplying the x's, not the function, is going to be a horizontal transformation. Now the question is this a stretch or a smoosh horizontally? Well, let's check up here. Let's check our rule. Where's our rule? All right, it's horizontal because it's being multiplied by the x. When a is, let's see, what did they, oh my goodness, why did they phrase it so weird? All right, here we go. When a is bigger than 1, it's a horizontal shrink. When a is between 0 and 1, it's a horizontal stretch. So the question is 1/3, where's 1/3? 1/3 is between 0 and 1, so this will be a horizontal stretch. Okay, horizontal stretch. And the horizontal stretch is going to be, this is where it says by a factor of 1 over a, where a is that number. So let's see. So what is, that's a weird question. What is 1 over 1 over 3? Does anyone know how to deal with a fraction within a fraction? That's weird. That's actually just equal to 3. All right, so it's a horizontal stretch by a factor of 3. Right? So watch what happens here. So here, it said the y-intercept stays the same. Here's the point 1. What is 3 times 1? Well, that's 3. So my new point is going to be there. Y-intercept stays the same. Y-intercept, there. Here's its x-coordinate is 2. What is 3 times 2? 6. So that means this point is going to be over 2, 4, 6. Right there. All right. Here, this point was at 3 for its x-coordinate, and 3 times 3 is 9. So this one's going to be, here's 3, here's 6, here's 9. All right, how about this one? Here's at -1. What's -1 times 3? -1 times 3 is -3. Right? Here's -2 for its x-coordinate. Multiply by 3 is going to be -6. So that's all the way over here. And so if I draw this line, I get a horizontal stretch when the value was between 0 and 1, right? And this was between 0 and 1. And then, like, you just kind of have to do a weird reciprocal thing to figure out what you multiply by. So there's a horizontal stretch. Let's do this one. Here's h of x. So for h of x, what do I know? The function is being multiplied by 3, so it's going to be a vertical transformation. The 3 that it's being multiplied by is bigger than 1, so is this a stretch or a smoosh vertically? And if we don't remember, we can always check. Well, bigger than 1, it's a stretch. Stretch. All right, stretch. So this is going to be a vertical stretch by a factor of 3. All right, so here's the y-intercept. Let's see, actually, ooh, it's an interesting question. Here it says the x-intercept stays the same. Good thing we checked, because I was going to say, I don't think this is going to stay the same. So here's my x-intercept. That stays the same. Here's a point over here. whoa. I'm on the purple line. I guess I should have done this on 2 graphs. Maybe not. We'll see. So here's the x-intercept of the purple graph, the original function. That stays the same. This has a y-coordinate of 1. Multiply that by 3. That's up here. This had a y-coordinate of 2. Multiply that by 3. That's now going to be at 6, so that's up here. This had a y-coordinate of 3. Multiply that by 3. That's going to be at 9. Right here, this had a y-coordinate of -2. Multiply that by 3. That's going to be at -6. Right, something like that. And let's draw this line. Draw this line all the time. All right. So we can see a vertical stretch by a factor of 3. So times 3 is what happened to those y coordinates. Whew, man, this does take actually a little bit longer to explain than I thought. But the good news is, once you get these transformations, it's going to help you out for the rest of your life. Because, yeah, that's the case. That's how reality works. Because tomorrow we're going to be doing transformations of absolute value functions. Hey, we still got time. Don't pack up yet. Yeah, don't worry, don't worry. Oh, wait, yeah, that's actually weird. Our clock is wrong. Yeah, it's 9:55. All right. We're time traveling here, internet friends. I can't wait. Maybe we'll make it to the future. Guys, what if our internet friends are watching this right now, and then, like, because of time travel, we caught up to them, and then we, like, show up at their house and we're in the future with them as they're watching this video being recorded? That would be so weird. Wow. Guys, we're time traveling. Our clock is just, like, spinning like crazy. Here, let's try to get this horizontal and vertical shrinks. If f of x equals x plus 2, graph the function and then describe the transformation of the function. Let me do this quick. Original function slope is 1. The intercept is 2. So let's see, up 2 right there. Bam, slope of 1. So that's going to be an up 1 over 1, up 1 over 1, up 1 over 1. Draw a line all the time. And there. And man, with that clock going fast, it's actually making me feel like I have to go faster. All right, there's my line. All right, let's graph g of x. G of x, let's see, the inside is being multiplied by 4. It's horizontal because it's affecting the x. Multiplying the x by a number bigger than 1 is not a stretch, it's a shrink. And it's by a factor of 1 over that number, okay? So of 1/4. That means it's going to be a quarter of the width that it originally was. So let me pick a point that's helpful. So here's 4 for its x coordinate, right? That's like 4 comma something, maybe 6. Yeah. This point is now going to be a quarter of its x value, x coordinate. So 1/4 of 4 is 1, right? Here is, let's see, let me pick ones that are nicely divisible by 4. Here's 8. What's 8 divided by 4? 8 divided by 4, or 8 times a quarter? 8 divided by 4 is 2, right? How about 0? What's 0 divided by 4 is still 0, so that stays in the same spot. How about -4? -4 divided by 4 is -1. And so this ends up being a horizontal shrink, like so and like so. So there's the horizontal shrink, where it is now 1/4 the scale. And let's do this last one, h of x. H of x, that looks like a V almost. There we go. 1/4 is being multiplied by the entire function, so it's vertical. It's a stretch because this number is less than 1 and greater than 0, so vertical shrink or shmoosh. Yeah, right, I'll use shmoosh there, by a factor of 1/4. So here we go, here's my original function. This point stays the same. Here, this one was at -4, a quarter of that is at 1 now. Here's a point at positive 4, so that's going to be 1/4 of 4 is 1. Where's a point that's 8 high? 4, 5, 6, 7, 8. Here, this one has a y-coordinate of 8. What's 8 divided by 4, friends? Come on, friends. 8 divided by 4. 8 divided by 4 is 2. So this is now right there. Now I noticed. So when I draw that line, it was a vertical smoosh where this is now 1/4 the height, and this is actually, yeah, 1/4 there as well. Whew. Wow, good sneeze right there. So I think that's all we'll have time for today. There are some more examples in the book that you can take a gander at. Oh, we were going to do multiple transformations. Blessed! Well, for the sake of our internet friends, I'll at least... Man, that is so weird how it does that. I get so much ghosting from my snipping tool here. So it is also possible to do multiple transformations simultaneously. And so we'll talk about that where, right, you translate horizontally, you stretch or shrink, right? You then can do vertical, all sorts of things. You can reflect, where we'll do multiple of those together. You'll see some of that when we go over the homework video tomorrow. Have a great day, friends. Bye-bye.